Warning, all attendees are in listen-only mode.
Good morning, everyone. My name is Angela Martinez, and I'd like to welcome you to today's webinar, an overview of hydraulics of water distribution networks, sponsored by BAYWORK. BAYWORK is a consortium of Bay Area water and wastewater utilities working together to ensure that we will have the reliable workforce needed to serve our customers and protect the environment. Before we get started, I would like to go over a few items so you know how to participate in today's event. We've taken a screenshot of the attendee interface. You should see a control panel in the upper right corner of your screen. GoToWebinar will automatically default to your computer's speaker system. If you would prefer to join over the phone, just select telephone in the audio pane and the dial-in information will be displayed. After logging on, your microphone will automatically be muted. You will have the opportunity to submit text questions to today's presenter by typing your questions into the questions pane of the control panel. You may send in your questions at any time during the presentation. We will collect these and try to address as many questions as we can during the short Q&A session in the middle of the presentation and the longer one at the end. Today's presentation will be recorded and will be viewable at baywork.org within the next 2 weeks. I would now like to introduce you to Robert Scott, the chair of BAYWORK's Staff Preparedness Subcommittee, who will be the moderator for today's webinar. Hello, Robert.
Hi, Angela, and good morning, everyone. I want to welcome you again to BAYWORK's webinar on an overview of hydraulic of water and distribution networks. We are so glad to have our presenter, Bassam Kassab, with us today. Bassam Kassab has been working as a hydraulic engineer at the Santa Clara Valley Water District since 2001. First in the Capital Projects Program, then in raw water operations, and currently he supervises the Groundwater Modeling Group, and he leads the Water District's efforts to comply with the Sustainable Groundwater Management Act. Bassam is also an adjunct faculty at San Jose State University, where he teaches water resources engineering. His research interests include steady flow in water distribution networks, hydraulic transients, deterministic and stochastic hill slope hydrology, flow of grains, as well as production and inventory management in operations research. And just to give you some additional information about our intriguing presenter, during his free time, Bassam teaches Spanish, which is his fourth language, and he writes screenplays and produces independent films. Isn't he an interesting fellow? Well, with no further ado, I'd like to turn it over to Bassam Kassab, our presenter for today. I'm going to give him control of the screen now.
Good morning. Good morning to those who are on the West Coast, and good afternoon for those who are on the East Coast or in other countries. I hear we have people even in Nigeria, so good evening. My name is Bassam Kassab, and today we're going to talk about the hydraulics of water distribution networks. But first, I'll start with some review of fundamental principles in order to get to talk about distribution networks. So this is the outline of our presentation. I'm going to discuss what's the difference between pressurized and open channel type flow in pipes, when we have uniform or non-uniform flow, and when we talk about steady and unsteady flow. And then I'll address the principles of hydraulics, conservation of mass principle, conservation of energy principle, and we won't talk much today about the conservation of momentum because it doesn't apply for steady flow in water distribution networks. We'll hint on it when we talk about hydraulic transients. And then I'll talk a little bit about AGL and EGL, and then we'll delve more into the water distribution network analysis and talk about the software available in the market, discuss pumps and turbines, hydraulic transients, and then we'll take your questions at the end. First, pressurized or open channel flow in a closed conduit. How do we know what type of flow we have? Let's observe the pipe on the left and the pipe on the right. In the pipe on the left side, we have the water is touching the soffit. That means the top of the pipe. So the pipe flow is under pressure here. But on the right side, you see that the water surface is not touching the soffit, the top of the pipe. That means the water is flowing like as if it were in an open channel, in a river, in a canal. You have air here on the top of the water surface. That means it's not under pressure. Okay? So in today's presentation, the focus will be on pressurized pipes, because ultimately we want to talk about water distribution networks. And flow in water distribution network, whether it's raw water or treated water, it's pressurized. But flow in sewage network, in a storm drain, it's typically not pressurized, unless when it goes under a highway and up, you have to pump it, that's when it becomes pressurized. But the focus today will be on pressurized pipe flow. Let's look at the first diagram on the left. You have laminar flow and you have turbine flow. Laminar flow is when you have very low velocities, such that all the streamlines, those red arrows, are parallel to the flow, parallel to your pipe. And there are nice straight lines. Typically they are bound by a parabola, and you see that at the wall you have almost zero velocity, actually zero velocity at the wall, and the maximum velocity will be around the middle of the pipe. Whereas when you have turbine flow, you have more like those eddies type flow, you don't have nice straight lines. So one way to find out what type of flow in a lab, for example, you can inject a dye at the beginning, a red drop of liquid, and then if the dye keeps on moving in a straight line, that means you are dealing with laminar flow. But if you inject the dye in this case, and then it's going to start to mix and disperse, and then it's going to fill the whole pipe and keeps on moving. The whole water is going to become red. That shows you that you have turbulent flow. So how is the flow in a pressurized pipe is driven? It's driven by the difference in head. For example, you can have a reservoir and a tank at the beginning and end of the pipe. If there is a difference in elevation in those reservoir and the tank, there is flow in that pipe, and it is under pressure. And in other cases, when you do not have those difference in head in the tank and the pipe, you use a pump. If you want to pump water from one level to another, you want to overcome that differential in head that's against the flow, the desired direction of the flow, use a pump, and in that case you also have pressurized flow. As opposed to the right-hand side, open channel flow is driven by gravity. Flow in this case is moving from left to right because the pipe is at a certain slope. It could be a very small inclination, but there is some slope, and that's what's driving the flow from left to right. When it comes to pressurized flow, we talk about Reynolds number. It's a dimensional number that's used to assess what kind of flow you have. Reynolds number will help us to discover whether we have laminar flow or transition zone flow or wholly turbulent flow, which you're going to see later in Moody diagram. Whereas on the right side, you have fluid number, another dimensional number that helps you decide whether the flow is subcritical, critical, or supercritical. Again, in more pressurized pipe flow today, in today's webinar, we're going to only talk about pressurized flow and Reynolds number. And when the flow, the water is touching the inside of the pipe, the wall of the pipe, there is friction between water and the wall of the pipe. And the friction is usually evaluated by a friction loss equation. It could be Darcy-Weisbach's equation, it could be Hazen-Williams equation, or Chessy's equation. Those are the three used equations for friction loss. But today we'll focus on Darcy-Weisbach equation in our webinar. Please do not confuse that with Manning's equation. Manning's equation is used and only used for open channel flow. You don't bring it to a pressurized pipe system. I mentioned Reynolds number is defined as the velocity in the pipe, velocity of water times the diameter over the kinematic viscosity. Basically, it's a ratio of inertia force to viscous force. So when the inertia force, the velocity of the flow in the pipe is small, when it's very small, the Reynolds number is less than 2,000, and you call that laminar. When it's larger, it's a large velocity, it overcomes the kinematic, the viscous forces here. That's when it becomes transitional or turbulent flow. So here are the cases. I apologize, this is hiding the value here. I'll fix it in the PowerPoint that is going to be posted later. But for laminar flow in case A here, what you see, Reynolds number is less than 2,000. That's when it is laminar flow. But for case B here, the Reynolds number can range from 4,000 to 800 million or more. That's when you have transitional zone flow or wholly turbulent zone flow. And you will see what I mean by those terms when I move to the next chart that many of you have seen, which is the Moody diagram, that helps you find the friction factor F that you use in Darcy-Weisbach equation. So here you look at Reynolds number at the bottom, which is VD over nu, and when it's less than 2,000 in this area here, it's laminar flow. But when it's higher than 4,000, up to 800 million, you end up with either a transition zone flow or wholly turbulent or complete turbulent flow. All right. So that diagram is used to be able to find F, the friction factor for the head loss equation. So if you have the velocity and the diameter of the pipe, you find Reynolds number. And then if you know the roughness of the pipe, epsilon, if you know the material, there are tables you find in books or online to help you find the epsilon, which is the roughness of the pipe. You divide it by the diameter, you get a dimensionless number called relative roughness. So if you know Reynolds number here, let's say 10,000, and you know relative roughness 0.02, you go up, you follow this curve, you meet here the value 10,000, and then you go straight across and you read the F value, which is 0.034. Remember, this is a logarithmic scale here. So F equals 0.034. So F could range from around 0.01 to around 0.08 or something. Robert, I think now it's a good time for a polling question. Could you please give them the first polling question?
All right. We have a question here for everyone. And the question is, in what capacity do you work with water? In what capacity do you work with water? Are you an operator, a contractor, engineer, maintenance technician, or other? I see answers coming in. So we'll allow a few more seconds for all the answers to come in. What capacity do you work with water? Operator, contractor, engineer, maintenance technician, or other? All right. Responses are still coming. Okay, we're going to close the poll in 5, 4, 3, 2, and 1. And I'll share the results with you.
So I see we have a little bit more than 50% engineers, 1/4 operators, 6% maintenance technicians, and we have 19% other. Could be a manager, could be people working in other capacities. But I see we have a mix. People who have seen that material and maybe they are taking it as a refresher now. Others who want to learn more about it, and I'm going to try to tailor this presentation to accommodate all. And as I said at the beginning, if I go through something quickly, you can always come back to BAYWORK website and look at the presentation at your own pace. I believe the video will be there too. Thank you, Robert. So now the next topic I'm going to address quickly is what's the difference between uniform and non-uniform and steady and unsteady. I find it all the time that some folks get those concepts confused a little bit. So uniform flow, there are constant flow characteristics like velocity with respect to space. When you have those velocities do not change with space, look at the diagram here. When I mean space, when the flow is going from left to right, in this case, that's your x-axis here. If the velocity is not changing from left to right, that's uniform flow. And that's typical from the pipe at the constant diameter. But what you see here in that manifold is you have a pipe, then a reducer, then a smaller pipe. So definitely here we expect that the velocity is not change because the area is changing from large area A1 to smaller area A2. So expect the velocity to be smaller here at E1, larger at E2. Since the flow characteristic like velocity has changed, that means that's what you are seeing here is non-uniform flow because it changes with space. So that's a non-uniform case. Not to confuse that with steady flow and unsteady flow. When we talk about steady, we are talking about time. When the flow or the velocity or the pressure doesn't change with the time, that's when we are talking about steady flow. And when it changes with time, whether abruptly, like in the transient case, or slowly over time, like when you have things changing over 24 hours. For example, consider a water distribution network. You have demand, and at night, most people are sleeping. There's less demand, so the flow in the system is small. Whereas in the morning, people wake up, they start using the showers or running their washing machine, and then the demand in the city becomes large, and the flow in the system becomes larger. So change over time. Something change over time, it's unsteady. But when it changes very rapidly, abruptly, that's transit. Hopefully we'll address it at the end if you have time. But when we talk about steady, that means things are constant. When in reality, things are not constant. But we do need the steady case when we are modeling a water distribution system because we want to understand, let's say, if we are doing the maximum daily flow, we care about that case. So we assume only that case and we model our system. We want to see results for maximum flow. Or we want to see what's going to happen, what's the maximum pressure we're going to encounter in the system or the minimum pressure for that particular case. And that's why when we do water distribution network analysis, we care about the steady case to start with, then we consider other cases. So I said there are conservation of mass principle and conservation of energy. And actually there's a third important principle in hydraulics, conservation of momentum. But when we talk about water distribution networks for the steady case, we only use the mass principle, conservation of mass as conservation of energy that I'm going to talk about now. The momentum will, you could use it when you are dealing with the design of a dam or a spillway, or in this case, when we deal with the transient flow, we are going to need the momentum equation when we touch on that later. But now let's remind you of those principles, conservation of mass principle. The differential equation is written as change in storage over time equals the flow in minus the flow out. What's coming into the system minus what's coming out. That's when you focus on one control volume. The control volume could be your whole network or it could be one junction. You decide on the control volume. And when we have a steady case, that means there's nothing changing over time. ds over dt equals 0, no change in storage. That's when we have what's coming into the system equals what's coming out. Inflow equals outflow. And you could have multiple inflows, should be equal to the summation of the multiple outflows. Like you see in the next diagram. Here you have two pipes intersecting, and that's a junction. So that's your control volume, CV. And you see what's coming in, Q1 and Q2, should be equal to what's coming out, Q3 and Q4. It's obvious here in this diagram. And by the way, hydraulics is very similar to electric circuits and transportation. Look at this as a transportation problem. All the cars coming in into an intersection should be equal to all the cars coming out. Q1 plus Q2 equals Q3 plus Q4. Now we jump to the more difficult principle, which is conservation of energy principle. When we're designing a pipe, I said we consider the steady state first. If we're dealing, let's say, with the maximum flow of the pipe, that's the case we care about. So we talk about that case only. And you write the energy equation. And the energy equation is written as 3 head terms. Instead of writing pressure in the units of pressure, we divide by gamma, which is the specific weight, to get the unit of a head, which is length, unit of length. It could be meter or feet. So you divide you are writing a problem, an equation from point 1 to point 2 here. So the pressure at point 1 over gamma plus the velocity head plus the elevation head V. In Bernoulli's theorem, you say the pressure at 1 plus V1 squared plus V1 equals the pressure term at 2 plus V2 squared over 2G plus V2. That's Bernoulli, because Bernoulli doesn't consider losses. But the general energy equation that I would like people to know, that you don't always use Bernoulli. You want to use the general equation that involves anything, any extra head you bring into the system, which is brought by the pump. The pump adds head to the system, whereas the turbine takes head out. Also the losses. The losses are taking the head out. So what you start with as the head here at 1, you can add the head of the turbine to it, and then what's left at point 2, because you lost the turbine head and you lost the losses in the system, which are friction losses and minor losses, and we'll talk about them in a second. So that's the general energy equation. And do not please refer to it as Bernoulli, because Bernoulli is for the only special case of no losses, and that's typical, for example, when you have a short distance, or like in a lab, when you have like a plastic pipe or glass pipe, you are doing some tests, you don't have much losses between point 1 and point 2. And the distance is very short in the lab. But in real life, when you have a significant length of pipe, you want to use the whole energy equation, because the friction losses here and the minor losses are not negligible. And this is for you later to come back to it if you want to understand the definition of each term: pressure head, elevation head, velocity head. Now, piezometric head means the pressure plus the elevation head. That's what you call piezometric. And people who are work in this field, especially operators and maintenance technicians, they see that word often, piezometric head, or mostly they call it hydraulic grade line, or HGL. So that term is important to know what it means, and it does not include the velocity. And it's not only the pressure, it's the pressure plus elevation of the pipe. So all the pipes should be measured from one datum. It could be a mean sea level that you consider, or it could be any arbitrary datum that you take. It doesn't matter, as long as all the points are measured from the same datum. So you have to add both to talk about the hydraulic grade line, or the piezometric head. Now, the total head involves one extra term, which is velocity squared over 2G, the velocity head. So in addition to the HGL here, P over gamma plus V, you have to add the velocity head, and that's what gives you all the energy grade line, the total energy grade line, or EGL. And the head losses, as I said, they could be friction loss and minor loss, and the turbine here head and pump head, all of them are part of the energy equation. Now, the friction loss, it results between the friction between fluid particles and the pipe wall. And I said at the beginning, we're going to only focus today on the Darcy-Weisbach equation. And that's the equation: the head loss due to friction equals a certain dimensional friction coefficient F that you get from Mooney diagram, multiplied by the length of the pipe over the diameter B, and then multiplied by the velocity head, which is V squared over 2G. G is the gravitational acceleration. Now, the minor head loss, it can be caused by a valve in your network, the entrance from a reservoir to a pipe, the exit from a pipe to a tank or a reservoir, the bend or elbow in a pipe, the expansion in a pipe, like the example before we saw the example of pipe contraction. It goes from large pipe to small pipe, you call that a reducer. So any change in the pipe, whether you put a valve or you change the direction of the pipe, that's going to cause some loss, because the streamlines are going to change direction and you lose energy there. And you want to account for that. To account for that, the minor loss expression is given as K value, some constant, depending on the valve or elbow or reducer or expansion. And there are tables for that. You multiply it by the velocity in the pipe square over 2G. That's how you get the head term, which is expressed in meter or in feet. Those are a few examples of K values for a pipe entrance, expansion, contraction, bend, or a valve. You can get values from tables like that you can find in books or online. And notice here, they talk about the valve wide open or half open. And when the valve is wide open, you have less losses. K is smaller. When it's half open, you get more losses. K becomes larger. And even when it's like open it just a little bit, the K could become very huge. And that's why you cannot really neglect the minor loss in this case. The word minor is, I consider it a misnomer. They call it minor, but it doesn't mean it's too small. It's just because it's localized. It happens in one location, like at the valve. Unlike the friction loss happens throughout the length of the pipe, over thousands of feet or meters. But when we talk about minor loss, it happens in one location, like at the valve. This is an example of a big valve. I believe that was a 9-foot valve here, around 3 meters. And you see the butterfly valve, how it turns. So when it's totally open, if the red disc is here, the losses will be less. But as you close the valve and the flow is passing through, it has more difficult time to pass through, so the K value becomes larger and larger. And that's an example of how the K value could change from 0.4 when it's totally open to 50% open, not like that's the degree, 45 degree open, that means 50%, so it becomes around 10, the K value. And when the degree of opening is just like 10 degrees, look at the K value, 1,000. It could go up to 4,000, even higher. So when you totally close the valve, your K value is infinity, but the velocity is 0. So that's important to know that K value becomes larger and larger as you close the valve. Now we're going to jump to a different topic, a little bit, not a different topic, but kind of talk about AGL and the EGL. Where do you see that? Well, many of you are familiar with SCADA. SCADA is the supervisory control and data acquisition system that many utilities have. They want to monitor the pressure in the pipe, the velocities. It could be monitoring what's happening at a treatment plant all over the network. The network could be the size of a city or a county or a country even. So there is an operator sitting in a room watching a big screen TV and looking at the SCADA system, seeing how the pressure is changing, how the velocity is changing, how the flow is changing, and not just the pressure in PSI, but also the head hydraulic grade line here. What's referring to, that's the hydraulic grade line. P over gamma plus the elevation Z. So that's where you see the hydraulic grade line always. As an operator, you see it on your screen, and it helps you make decisions whether to close the valve, open a valve, turn on a pump, etc. And yes, let me jump to the next screen to give you an example here. Again, the energy grade line is P over gamma plus D squared over 2G. And then the hydraulic grade line is only P squared over gamma plus D. So let's look at this network, and there'll be polling questions after that. So be ready, please, to answer them. We have a network here, and I'm not going to tell you whether the flow is going from left to right or right to left, because I'm not telling you what's this box, what does it represent. But what I'm showing you is the energy grade line here in dashed line, and the hydraulic grade line, HGL, in dotted line. Do you see them here? Well, the first question, because I would like you to test your knowledge, is to look at that distance between the two arrows at profile X. Let profile X go up, and you are going to see those two arrows. That distance between the two arrows, what does it represent? And I'll pass it to Robert to ask you the first question.
Here we go. What does the distance between the two arrows in the diagram represent? Please think about that and give us your answers, please. Okay, I see answers coming in. All right, we just all trying to learn. If you're not, you don't know, just take a wild guess.
We won't know who said what, so go for it.
All right, we'll give you a few more seconds. Great, great. Come on, go ahead and answer. Even if you're not sure, take your best guess. We would like full participation if we can get it. All right, I'm going to be closing the question in 5, 4, 3, 2, and 1. And here are our results.
Well, we have 3/4 of the people voted. That's great. Thank you for participating. I know some of you are sitting in a conference room with other people, so you only got one vote. But we see that, well, we do know that the majority is not always correct, but in this case, the majority is correct. So Robert, the answer is 47 velocity head. That's the difference between that line, the energy grade line, and the hydraulic grade line. That little distance here represents the velocity head, which is when you subtract the energy grade line from the hydraulic grade line from the energy grade line, the difference is velocity squared over 2g, which is called velocity head, as I said earlier. Now, the second question is, examine what's that elevation H. Is it the head loss in a turbine or the head gain in a pump? Well, you are not sure whether this box is a pump or a turbine, and it's your now your role to guess what it is. If you think about the diagram, you may. So I didn't tell you whether H is head gain in the pump or head loss in the turbine. So I don't want to tell you whether this box is a turbine and pump, and that's the third question the trouble is going to ask you.
All right. Here's the next question. What does the box in the diagram represent? Is it a valve, a pump, a turbine, or Pandora's box? Take your guess. If you're not sure, again, we'd like full participation if we can get it. All right, we have answers coming in. Okay. What does the box in the diagram represent? A valve, a pump, a turbine, or Pandora's box? All right. You'll see some answers coming. We'll close it in a few seconds here. All right, we'll close the poll in 5, 4, 3, 2, and 1. I'll share the results.
Well, Robert, is the majority always correct?
Not
the
always.
Majority is always right?
Not always.
Well, in that case, the majority isn't correct. Well, let's see why it's not a pump. Yes, you have seen maybe that diagram before. When you have a pump, you could have a flow from right to left, and the pump is able to lift water up. That's true. But the only reason that's not correct in this case is because of energy grade line and hydraulic grade line, the way they are drawn. If assume like you thought it's going to be a pump, that means you are thinking that the flow is coming from this low reservoir and being pumped up. Well, when it goes this way, the flow is going this way. Look at the EGL. It seems like it's gaining energy. Look, as the flow moves in this pipe, energy grade line, EGL, is becoming larger and larger. And you cannot gain energy while you are flowing in a pipe. When water is flowing in a pipe, it has to lose energy because of friction. So that's why you want to rule out pump here. But the other answers, let's look at the turbine answer. If flow is going from the left reservoir to the right reservoir, well, it's correct because the pipe here is you are moving from left to right, and as you move from left to right, the energy is dropping, and that's what happens with friction loss. The friction loss happens all over the pipe, and as you move from left to right, the energy grade line has to drop. And then at the turbine, it drops substantially because the turbine takes all the hydraulic pressure and converts it into electric, it takes the hydraulic power and converts it into electric power. So that's what the turbine does. So that's why you lose all that pressure here, and then you continue to lose energy grade line in the pipe. But I want to say that the valve question answer is not totally wrong because
excuse me,
yes.
Bassam.
Yes.
They didn't see your explanation. If you can do that again. I didn't switch the screen over. My bad.
Okay.
So explain why.
Okay. I can explain that. And the third question, the last question I can answer, will explain it more. So why it's not a pump? It's not a pump because if it were a pump, let's say if it were a pump, but that's wrong. Look at it. If the flow is coming from the right side and going to the left side, and then it's coming this way, and the pump takes it up, and then how can a flow go from the pump to the reservoir on the left, well, if it's going this way, you have to lose energy due to friction. But what you see on the diagram here, the EGL, if water is flowing that way in the pipe from right to left, EGL is kind of gaining energy. Well, you cannot gain energy as you move in a pipe. When you move in a pipe, you have to lose energy, and that's why this cannot be a pump. Well, it can be a turbine, because if you are moving from the left reservoir to the right one, as you move into the pipe here, energy gradient is dropping, and that's typical when you have friction loss in the pipe. As you're moving from left to right, the energy gradient is going to drop, and then when it arrives to the turbine, it's going to drop abruptly because the turbine takes all the hydraulic power and converts it, most of the electric power, hydraulic power, and converts it to electric power. So you have a big drop in the turbine, big drop in head, then the water continues losing energy to get to the reservoir. However, those who said turbine are correct, but those who said that are not totally correct, because this could have been a valve, and if it's closed, kind of only open by 3 degrees or 10 degrees or 20 degrees, you could have a huge drop in head. So that could be also a possibility to have a valve here. So the answer could be either a turbine or a valve. All right. Can you, Robert, go to the last question? And this one, everyone should get to try it if they pay attention to what I said now.
All right. Here we go. Here's the question. What is the flow direction in the system? Is the flow going from left to right? Is the flow going from right to left? Or does the flow oscillate back and forth? Or can you not tell based on the given information? What is the flow direction? Okay, I see answers coming in. All right. Still see some answers coming. We'll give it a few more seconds. What is the flow direction in the system? Left to right, right to left, oscillating back and forth, or cannot tell by given information? All right, I'll close the poll in 5, 4, 3, 2, and 1. And I'll share the results.
So the first answer is the correct answer. It goes from left to right. And the given information here, because I gave you the HGL and EGL, that's enough for you to know what's the direction of the flow. And please take that into consideration in the future. If you are an operator looking at your SCADA screen and you see the head on one side higher than the head on the other, use that information to infer about the flow direction. So we'll go to the next slide now. And we'll want to talk about water distribution networks. Well, many of you know that nowadays water distribution network is done using some software that you can buy or find free online. But let's go back to the basics first. I would like you to understand the basics before you use those and how everything started in the 1930s. So let's consider a simple network. It's formed of 5 pipes. Can I see my screen? Do I have sharing? Okay,
yes.
Awesome. So you have 5 pipes in the network: pipe 1, pipe 2, pipe 3, pipe 4, pipe 5. You have 1 reservoir here and 1 tank there, A and B. You have a pump. And those arrows here represent the demand. That means how much water is coming out of the system to the certain areas of town. And if you have, you know the demand, you know the characteristic of the pump, you know the elevation of the reservoir and the tank. Now, how much are the flows in the system? It's not that easy to guess because you have a looping system here, and you cannot solve that just looking at conservation of mass at each node. So you need to analyze that network. And how many unknowns do we have, flows or velocities? Let's say we're looking at velocities here. You have velocity pipe 1, 2, 3, 4, and 5. You have 5 unknown velocities. Or flows, it doesn't matter, are related velocities and flows. So you have 5 unknowns. And as you have seen when you were in maybe middle school, when you have one equation for one unknown. If you want to have a deterministic equation, each equation should have one unknown only. If you have two unknowns, you need two equations. And if you have five unknowns, you need five equations. So here in this case, we need five equations to solve for this simple problem with 5 pipes. So what are those equations? You can write the conservation of mass here at node 1. Conservation of mass, like we saw at the beginning, is the flow coming in equals the flow coming out. That means Q1 equals Q2 plus Q3. Same thing, you write the conservation of mass at node 2, and you write it at node 3. Those are three equations. They are linear equations. So the Q is to the power 1. Those are linear equations. But we need two more equations. So we have to go to the energy equation. And when you write the energy equation, it's not linear because it has the velocity square. It has that term velocity square. So it's not linear. Now we have a system of 5 equations. 3 of them are linear, 2 of them are nonlinear. That's not fun to solve. So let's look at the energy equation. How do you write it from? You can write it from A to B, from reservoir A to reservoir B, passing by the pump, pipe 1, pipe 2, and pipe 5. That's one equation. You can write it from reservoir A to B, but taking another route. It's like driving. You can choose to take pipe 2, or you can choose to take another route, pipe 3 and pipe 4. But then you can write the second time the energy equation from A to through the pump, pipe 1, pipe 3, pipe 4, pipe 5, and until you get to tank B. So those are your 5 equations. One of you out there may say, well, I can write it around the loop. And yes, you can. But when you do that, you cannot write 3 equations that energy equations in this case, because one of them is redundant. One of them can be deduced from others. And you do not add an equation that's redundant mathematically. So now let's not delve too much into math. Let's just tell you, you have 3 equations for continuity, 2 energy equations. They are nonlinear. So how to solve a system of nonlinear equations? Let's see how people have done it since the beginning of the 20th century. Well, before even Hardy and Cross developed a method called Hardy-Cross method, hydraulic engineers used to solve hydraulic networks by building a similar electric network in a lab, and instead of a pipe with a certain resistance, they would represent it by a resistance. If the pipe is 1,000 feet long, they're represented, let's say, by resistance 10 inch long, and if the pipe is half that size, they put a resistance half that size, etc. So they model the water network based on an electric network in a lab, and that's how they had that idea how much flow goes into each pipe, depending on what they found the current to be in the electric network. But the next thing came out in 1936 by Hardy-Cross. It's a method. Some of you are taking fluid classes. I've seen it. It's manual method. It's too much hassle when it's a large network. You are talking 10, 20, 100, 500,000 pipes. You could spend your lifetime trying to solve this network using Hardy-Cross. So in the 60s and 70s, many numerical methods were developed, some of them based on Newton-Raphson technique, so basically numerical analysis, and those require iteration. And by then, the computers were not as fast as today, so if they stopped at 100 iterations, sometimes they face problem with converging the solution. Maybe they should have run thousands of iterations, and they were not capable. So because those methods, the iterative methods, were not perfect back then, especially because of the computers were not that powerful, in the 80s, they came up with the linearization method. It's an approximation, but they linearized the system of 5 equations. And in 96, me and Basha, we came up with a method to solve the system in a direct way, mathematical way, no iterations, just by solving the zero order matrix here. A represents a matrix. In this case, it's 5 by 5 matrix, but you could go about to 1,000 by 1,000 matrix. And then you get the solution, plug it in here, and find the first order solution, second order, third order, and then you sum the 4 solutions, and you boom, and you get the final answer. That's more like manual method. Of course, it's easier if you code it, but it's not by iteration. But most of the software we see in the market today, they are based on the iterative methods, especially nowadays in the 90s and 2000 and 2010, like you have the fast computers, you can do thousands of iterations within 1 second. So that's why all the softwares now they are based on this numerical method. And that algorithm, like I said, it's numerical. You can use that for steady state simulation for finding one set of flows or velocities in your network. But again, those software allow you to do what's called EPS, Expanded Theory simulation. And let's say you care about over 1 day what's going to happen in your system. The flow changes, the demand changes during the day, so the flow changes, the velocity changes during the day, the pressure changes. But you don't consider that a transient problem. It's just a series of 24 steady problems if you want to run it every hour. Or if you want to run it every 15 minutes or 5 minutes, that's fine. You run more steady state solutions. And all those software are capable of doing that. This is very useful when you talk about water quality in pipes, tracing contaminants, water age. If you want to answer those questions, you want to do extended period simulation. There's a free software out there by the EPA, the Environmental Protection Agency. It's called EPANet. You can find it for free. And nowadays it has a nice GUI, graphic user interface. But there are commercial software that you could buy. Here where I work at the Water District, we use H2O.net. There's Infomap from the same company. It's based on GIS. There's WaterCAD, WaterGems from a different company, etc. There are many software out there. So I'm not here to promote one software, but I'm saying they all do almost the same thing. They give you the correct results, but they have different bells and whistles. The graphic interface could be different from one to another, nicer, more tables, more graphs at the end for the results, nicer reports. Some work in GIS environment, and some you can add the hydraulic transit software or search software to it. This is an example of a model I built here for the Santa Clara Valley, which is the heart of Silicon Valley in California. That's our water system. It extends from outside the county here in San Luis Reservoir, and it comes to the county. And you see here it's skeletonized. That means instead of putting all the pipes, small and big, and paying attention to every detail, we focus on the skeleton, the main part of the network. And that's what we are concerned about. So only we put the important pipe in a network, in a model. And that's what you call skeleton, water distribution network. And you can see all the pipes here, and you can see that because I'm not using a GIS map in the background, I have the liberty to expand a pump station. The pump station could have the size of a building, but I'm expanding it, making it huge here compared to the pipe that are like miles and miles long, because I want to see the details inside each pump station. That's why I'm expanding it. And here I'm focusing on one pump station. You can see we can put pumps in parallel. We can put valves to control the pumps, close, shut down the valve, etc. So you can put many details in the model. But the important part in the model is to calibrate it. How good is, if it's well calibrated, it's useful. If it's not well calibrated, maybe you're better off not having a model if you don't want to calibrate it well. And pump curves, I know many engineers and operators can ask me about pump curves. They are like a little bit confusing. That's why I want to dedicate a couple of slides to talk about pump curves here and share my understanding of pumps with you. So a pump characteristic curve, what I'm showing you here with the mouse, it's called pump head curve or pump characteristic curve. It comes from the manufacturer. Basically, it's a plot of the head of the pump, the head that the pump generates, to the flow. So that's the curve. When the flow is very small or even zero, it's called shut-off head here, this point. And then it goes down the head. The more the flow, the less the head the pump can get. And that makes sense, right? So the pump curve comes with the pump when you buy it from the manufacturer. But if you have one of those big pumps that you are using for a city or a town, you want to calibrate it every year to make sure whether that curve has changed or not because of the operation of the pump, and things may change. That's why technicians or engineers calibrate the pump typically every year. And that's one thing. Okay, you get that pump curve, but how does it help you? You need to understand your system. And by system, it could be the whole water distribution network, or it could be a simple system like I showed you earlier here. If you have like a 2 reservoir and pump between them and 3 pipes here, so when you write that energy equation from point A to point B, that's an equation, it's describing your system. And that's when you bring it here and plot it. Plot the head of the pump versus the flow. And I'm going to show in the next slide how it looks like. The head of the pump is related to the difference in elevation between the reservoirs, and you add to it the friction loss and the minor loss, because the pump has to overcome all of that, friction loss and minor loss, in addition to the elevation between the reservoirs. Back to this. So that's Z1 minus Z2 or Z2 minus Z1. It's called static lift. The pump has to overcome that and all the losses. So that's the system curve that's based on the equation I just showed you. And I'm going to flip to that now in a second. That's a parabola. That's a branch of a parabola here. That's the minimum of the parabola and keeps on going up. So that system curve meets the pump characteristic curve here at a point called operating point. Well, that's the operating point for that situation when you have the reservoirs at those elevations. But when the tank elevation changes, that system curve is going to change. We're going to have a different curve like that, or different curve like that. When the Z2 minus Z1 changes, the curve could go down, it could go up, so you get a new operating point. So the operating point is non-unique. So it's not unique. Know that, please. So this is only for one case, one study case that I'm showing you. It has one point. But the operating point could be anywhere on the pump curve. Now, is it the most efficient point? Let's see. Well, you need to have an efficiency curve that you get from the manufacturer, or you find it yourself by doing some pump tests. And that's the efficiency curve that you can see on the right side here, pump efficiency. So ideally, you would like to run at the highest efficiency, but not always the operating point is the best efficiency point. If the operating point moves here, and if maximum efficiency is here, that means you are not running the pump at best efficiency. But you can't do much about that. You have to run the pump based on what the system needs. So it could be sometimes running at less than optimal efficiency. So as I said earlier, that's how you build the pump system curve, by writing energy equation, simplifying it, putting the pump on one side and the velocities or flows on the other, and you plot it as a parabola. And usually it's like slowly increasing, and where it intersects the pump curve, that's your operating point for that particular case, for one study case. Now, some people ask, well, what if one pump is not enough? What should we do? Well, should we buy a larger pump? Should we add another pump? Should we add it in parallel or in series? Well, let's talk about that. As I've shown you here in the diagram that I drawn manually, so we can have, you can put 2 pumps in series. And when you put the 2 pumps in series, well, let's see what happens to your pump curve. Here in blue, you can see the pump curve, pump characteristic curve for one pump. But when you add another pump in series, you are gonna get more head out of this pump, but for the same flow, because the same Q is going still through the same pump, theoretically. So when you have one Q here, it gives you this head if you have one pump. But the same Q, if you add another pump, it will give you double the head. So even for the shutoff head, it will double. Every point here on the pump will double. So that's how you plot the new pump curve for 2 pumps in series. And now if you have a system curve, you'll see where it crosses. If the system curve starts here, it will cross there. If your system curve starts here, that means one pump is not enough. That's why you add the second pump, and you will plot the system curve and see where they meet here. So that's the proof that if your system curve starts here, one pump is not going to be enough. You need another one in series. But sometimes you need more flow. Now you don't need more head. If the demand in the system, projected demand in the future is going to be larger, so you need more flow to come out, you can add another same size pump or another small pump. It's up to you. But the diagram here is for another same size pump. If you have one pump, that's the pump curve. But if you have 2 pumps in parallel, you are going to have double the flow with the same head. because they had differential here between this node and that node is still the same for the pump. One pump or two pump, it's the same head differential, but you double the flow. So you can go back to the diagram, think about it, think about if you put 3 pumps, 4 pumps, if you mix 2 in series and 2 in parallel, and how it's going to work out. If you put 4 pumps, 2 series and 2 series, and then you join them in parallel, how you are going to get the new diagram. I'll be happy if you plot it and email it to me. I'm going to provide my email at the end. So your homework is to plot, you have 2 pumps in series, another 2 pumps in series, join them together in a parallel scheme, and then tell me what the new pump curve looks like. So I also got the question about the issue of efficiency of the pump. So here I made a simple diagram to show you what's the total efficiency of a pump, and if you care to know about the brake horsepower or the motor power, how you find them by knowing individual efficiencies. Or if you do know the motor power or brake horsepower, you can compute the efficiency in between. And to compute any efficiency, it's simple. Always the efficiency is the output power over the input power, never the input over the output. Why did I say the output over the input? I didn't have all questions for that, but I'm going to ask you, think about it for a second. Why is it output over input, not input over output? Because the output power is always less than the input. Because in your system, you lose power. You do not gain power in a system like that. So the efficiency has to be less than 1. Since the efficiency is less than 1, it's always the output power over the input. So I plotted that diagram in this way. Because the input power is the electric power, it's causing the pump to run, the overall efficiency would get you to the hydraulic power. The hydraulic power has to be less than the electric power because you lose power in the system. And the total efficiency is the output power over the input power, which is the hydraulic power over the electric power. And this is the multiplication of the smaller efficiencies here. You do not add those efficiencies because you end up with a number larger than 1. You have to multiply them. And the E-motor, for example, is the brake horsepower over the motor power. Always the output over the input. And the arrow that I drew here is to represent the direction of flow, of power movement, I mean. Now turbines, again, the turbine is basically the opposite of the pump. The pump generates power, the turbine takes power. The turbine takes the hydraulic power to give the electric power. And that's what I drew here. That's a turbine that's spinning. It takes in the hydraulic power from the drop of water, from the water dropping on the blades. They turn, they spin, and then it ends up generating electricity. So that's the output, that's the input. So the efficiency of the turbine is the electric power of the hydraulic power. It's the opposite than the pump. And the hydraulic power of the turbine is given by this definition: specific weight of water, flow times head of the turbine. It seems we still have 5 minutes. I can go quickly over the hydraulic transients. Can I?
Yes, go ahead.
Okay, because I had got some questions before the webinar. People are interested in hydraulic transients. So the transient can happen when, for example, look at this tank here, and there's the pipe, and there's the valve. If the valve is shut off quickly, abruptly, or even within a few seconds, it could be done automatically or by hand. If you do that quickly, you may cause a transient. Why? Because the flow is coming here at high speed, and then you drop the valve closed. You shut it off. The flow is going to hit the wall here. So it's you have a wave going back and forth and back and forth, and the pressure could be going positive and negative, and that could deteriorate your pipe, or sometimes break it if the transit is too big. So a valve, shutting off a valve, or even opening it abruptly could cause that. Stopping or starting a pump or a turbine can do that. Any event like power outage can cause that. So transit can happen in the system. And that's why you want to have to understand the severity to see maybe you have to design the pipe thicker or different material to be able to take such transients. And also to tell your operators, please do not shut the valve in less than 10 seconds or 20 seconds. Take the time to shut it off so you don't generate a large transient. To solve the transit problem, there are 2 governing equations. The conservation of mass equation that you see here as a partial differential equation, that I'm not going to go into that, and the momentum equation. So those 2 nonlinear differential equations are difficult to solve, And that's how people have done them over the past. There was the arithmetic method, manual method, approximation by Jagoski in the beginning of the 20th century. Then there was the method of characteristic, which I've shown here, that you use that kind of scheme with boundary conditions, with the initial condition here and the boundary condition here on left and right, and to be able to find everything that happens in between with those waves, the pressure, we are looking for that pressure at point P. And that's nice when you program it. That's what I have done it. I've done that in order to compare to the method that I developed later. And so that's basically the numerical solution. That's mostly used the method of characteristics. Some people came with the wave plane analysis method. There was an approximation method again in the 70s. And then in the 90s, I came with the perturbation method. It's totally different scheme than the one I mentioned earlier, because we are dealing here with partial differential equation, but with the same mathematical concept, I was able to solve the transit problem mathematically. And you can see here my solutions, how they match with the numerical solution, which is here. That's for instantaneous pipe closure. When you close the valve instantaneously, you can see the positive pressure and negative, positive and negative, how it propagates to the system. And when you do a linear closure over time, you get a reduction in the transient. And when you do exponential closure for the valve, you can even get less transient. But you'll always get some transit when you're closing a valve. But that's why my advice is to always close the valve slowly. And here from a software, it's coming, it's showing what the software does versus the method of characteristic, that they have a good match. And here's a different case than the one I showed you earlier. It's not just a valve closing, but you can see how the transient oscillates, and the pressure could go up and down, up and down, up and down, until it subsides over time. And how you deal with transit in a pipe? As I said, the pipe has to be, the thickness and the grade of the pipe has to be suitable for the transient. You can minimize the effect of the transient by having a surge tank or an air surge tank like this, air chamber, same idea, but with the air chamber you have it's closed on the top and the air gets compressed here. But with the surge tank, the water level can go up and down. So you install that in your system, so when you have a transient, the surge tank or the air chamber can take most of the shock. But you can prevent that by slowly or opening, closing the valve, slowly closing a fire hydrant, and ramp up the speed of the pump. And design a network with small velocities, because with the high velocities, the transit will be more severe. And there are many software for hydraulic transients. I'm only familiar with those two, H2O surge and info surge. Those are, this is an add-on for H2O net, and this is an add-on for info water, which uses GIS environment. But there are many others out there in the market. All are good. You just need to learn one of them and learn it well. And again, my advice is to calibrate your network well first before you go into the surge analysis. It has to be calibrated for steady state before even you start doing the surge analysis. And those are the references I use, my papers and a couple of books. And this is my contact information. If you have a question, or if you want to answer the question about the 4 pumps, 2 in series and 2 in series, you put them in parallel, you get 4 pumps. What's the pump curve? And now it's back with Robert. I believe we have now Q&A session.
Yes. Sorry, everyone. We're over a little bit, but we want to make sure we get you the information. And we want to answer a few of your questions now. We'll go maybe another 5 minutes, and hopefully you'll be able to stay with us. Again, we apologize for going over. But here's a few of the questions that have come in so far. Bassam, here's the question. Is there a difference in losses between threaded valves and flanged valves?
Yeah, there is some difference, and you would want to go to tabulated values for the K values to see if the K is going to make any difference. But again, when the valve is fully open, the K is very small, and you may find that the values that you see tabulated online or in a book are very small Ks and could be similar. But the issue is when you close the valve partially, that's when K becomes large.
All right. All right. I'm going to take one more question here and then we'll close out. Why is the EGL equal to the water surface on the left but not on the right? So suppose they was referring to your diagram. Why is the EGL equal to the water surface on the left but not on the right?
Okay, the EGL on the left, first of all, the velocity in a tank or pipe at the surface is negligible because the surface is moving very slowly. And the pressure is zero because open to the atmosphere. The gauge pressure is zero. You only have the atmospheric pressure. So since we are dealing with gauge pressure in our energy equation, we consider the pressure to be zero. So what's left there on the left side is the elevation of the surface of the water. Okay? And then when you move into the pipe, you have a little bit of entrance loss. But then on the right side, when the pipe ends before you enter the reservoir, you still have a velocity head. And when you enter the reservoir, not you, I mean the water particle enters. Can
we show the diagram again?
Okay, I have access still to my PowerPoint, then I can show it. That would be easier than describing it. Thank you. So here, as I said, because the energy deadline, P over gamma is equal to 0 here, and V square equals 0 because the water surface is hardly moving. And then only here the EGR represents the elevation of that water surface. But when you get to that point here on the right side, P over gamma is 0. Here you have Z, but you still have some velocity in the pipe here when it enters the tank. So the velocity is large in the pipe, and that's what's represented here as the V square over 2G. You can see the HGL touches the surface of the water, because HGL is P over gamma plus Z. P over gamma here is 0, and you have the elevation Z. That's why the HGL is 0. But since you have high velocity here entering, you have that level here. But once you enter into the tank, you have the exit loss, which is equal to V square over 2G. Then the whole V square over 2G is going to drop immediately. So once your particle is inside of the tank, and then it's being dissipated, all the energy gets dissipated here, and you lose that V square over 2G. But the reason it's higher is because just before the water enters the tank, it is at high velocity, V square over 2G. That's why it's represented here. And that's correct, the diagram.
All right. Okay, well then that's all of our questions. Again, we apologize for going over for you. And if you have any more questions, you can submit those to Bassam as well. I want to also say that Bassam has agreed to do another webinar for us in the future that's related to hydraulics and hydrology. So stay tuned for that. I want to thank Bassam for presenting such great information and sharing this great experience with us. And I want to thank all of you for joining us today. We want all of you to be pleased to please stay tuned for other BAYWORK events, and we invite you to our website at baywork.org. Also, please know that the recording of this webinar will be posted at baywork.org within the next 2 weeks. Additionally, we will email contact certificates to those who answered yes to the questions regarding them on the registration form. Lastly, we really want to know your thoughts about this webinar. Please take a moment to complete the survey you will receive immediately after we are done. It is only 3 questions. Do you have any final words, Bassam?
I want to thank BAYWORK for having me for this webinar. Thank you, Robert, and thank you, Angela Martinez. I just want to iterate that calibration of a water distribution network is important, but it depends on the use of your network that decides how much you are going to go deep into the calibration. Is it used for designing your pipe, only finding the pressures in your pipe, or day-to-day operations? The use of the network, the purpose of the model will decide how much effort you have to put in your calibration. And thank you all very much for attending this webinar.
Well, we thank you, Bassam, again, and appreciate you doing this today. On behalf of BAYWORK, thanks again, everyone, for joining us. Please have a great rest of the day and rest of the week. Until next time, goodbye.